Here we are again. Good evening. It's a beautiful, gorgeous summer night in New York, and here this place is full of people who want to talk about holograms. And wow, you know, World Science Festival is so great. My name is John Hockenberry. First of all, I'm the college dropout news guy who's going to hang out with Nobel physicists tonight. Perfect for this job. Oh my God. How did I get here? Seriously. You know, we think of, this season as the World Science Festival. It's the beginning of June. The weather starts to get great. You know, tonight at the Brooklyn Bridge Park, it's supposed to be one of the best viewing nights in New York. And there aren't many really fabulous viewing nights in New York, so I urge you to do that. I mean, it's a beautiful, clear night. Everybody's out in their summer. It's kind of like prom season. We think of the World Science Festival as the prom for all the scientists who maybe didn't get any dates, didn't know there was a prom. And I actually polled our panel tonight. 3 clearly did not go to the prom, didn't want to talk about it, and 1 didn't remember at all. You may be able to figure out who is who tonight. I'm actually perfect for this gig for another reason, because I actually inadvertently helped to solve one of the most serious problems in physics back in the 1970s. I was on a team that helped to do that. I was enrolled at the University of Chicago as an undergraduate, and I tested into the top science section, basically junior year of science in my freshman year. And it was taught by a protege of David Schramm, one of the Nobel laureates at the University of Chicago, the late David Schramm, brilliant physicist, and part of the University of Chicago program, which gave us Enrico Fermi and so many others, and Chandrasekhar, and I was in this program and very excited. I go to the first lecture, and it was taught by one of these proteges, a Central European fellow. I can't remember his name now, and it will become clear why. He said, hello everyone, it's great to see all of you here. We have a very serious problem in physics. The problem is, it's a simple problem, but a serious problem. It is too many physicists. And so in this course, if you're getting B minus, you'll get F. If you're doing B plus A, you will get A. I went into the news business and thereby helped to solve the very serious problem in physics of too many physicists. So, and a lot of the panelists tonight are possibly grateful for that. So you are here to talk about and to listen to one of the most exciting, fascinating, also difficult principles that's now being kicked around in physics and cosmology, the holographic effect. And it involves a couple of concepts that actually we have a lot of intuitive sort of sense of. And I want to present 2 of those tonight before we introduce the panel and get started here. One is the idea of information. Information. We think we know what information is, right? Information is very, very, like, you know, here you go, information, right? Now that isn't the New York subway system, right? But it is enough information to specify how to get from point A to point B, and if you understand how to read the subway map, you can get from point A to point B. The information isn't exactly the same as the subway, but if you don't have the information, the subway is useless to you. And somehow it sort of maps directly, I mean, it is a map, right? It maps directly onto the subway. And of course now, the subway map, nobody has one of these, right? It's all on your smartphone, which means it's stored on a tiny piece of silicon. And so therefore, what the volume of this can actually be mapped directly to a volume, a 1/1,000,000th the size. Take, for example, this. Anybody got one of these anymore? No. I mean, this specifies the number of synonyms. I don't know what the hell it actually is, but it's a thesaurus, and it actually also fits in a tiny piece of code in Microsoft Word. We got here just the A to M's, okay, Oxford Shorter English Dictionary. Information. I'm going to set it over here just to remind you of what information is all about. Now, information, the dictionary, isn't the English language, right? The space, the universe of the English language is all you people talking. Will you talk now? Just talk. Just turn to your neighbor and say hello. How you doing? right there. See, that is the space called, that is the universe of the English language that you are hearing. It is not the same as this book, but it sort of maps on to this book. And there's enough information in this book to make predictions about what it is that you're saying, so that if you actually talk to me, I know what the hell it is that you're saying. Unfortunately, I probably won't know what the hell it is most of the panelists are saying tonight, so I may need your help with that. Nevertheless, there is information in what they say. The information maps onto a space where we can make predictions. It is information that allows us to be conscious beings. It is information that allows us to be living beings if you think of DNA as information. Now, the information we're going to talk about tonight is much more complicated, but the idea of information as a map, as a specification of a much bigger space, is sort of the beginnings of what we're talking about here. Now, the other thing is holograms. Right? You know, clap if you know what a hologram is. Right? Hologram, okay. All right. I should have said, clap if you think you know what a hologram is. Yeah. Let me introduce our panel. Please welcome Raphael Bousso. Let me tell you a few things about Raphael. Raphael Bousso is a theoretical physicist at the University of California, Berkeley. He's recognized for discovering the general relation between curved geometry of space-time and its information content, a key idea of the holographic principle. Please welcome our next panelist, Herman Verlinde. Herman Verlinde is a physics professor at Princeton University. In 1988, Verlinde received his PhD under the supervision of Gerard 't Hooft. Verlinde is renowned for his contributions to string theory and its application in particle physics, cosmology, and black hole physics. Some of his current work explores gravity in the context of the holographic principle. Our next panel is indeed Nobel Prize winner Gerard 't Hooft. Gerard 't Hooft received the 1999 Nobel Prize in Physics for his doctorate work in theoretical physics. He's a professor of physics, and of his many achievements, he was the first to propose the idea that would later become known as the holographic principle. And finally, our fourth panelist, Leonard Susskind. Professor Susskind is professor of theoretical physics at Stanford University and the first to give a more precise interpretation of the holographic principle using string theory. He's well known for his book on the topic of the holographic principle, The Black Hole War, My Battle with Stephen Hawking to Make the World Safer for Quantum Mechanics. It's a fantastic book. I highly recommend it. Please welcome the panel.
Back in the early 70s, Stephen Hawking wrote down an astonishing equation. It would include relativity, it would include quantum mechanics, and it would include information. Hawking's rather simple equation brought us a step closer to understanding the relationship of quantum physics and black holes.
When an object crosses over the edge of a black hole, its event horizon, the object enters a realm basically of empty space, of darkness. And it continues to be dragged toward the center of the black hole, toward what we call the singularity, where it gets crushed out of existence. Every object, in some sense, contains information because it contains a very specific arrangement of particles. So where is the information that describes the arrangement of those particles? Where does it go?
Hawking's description of this process was that the energy remains, but the information disappears.
For many years, for decades, people wondered, is Hawking right? Is the information obliterated and disappears from the universe, or is it still there and perhaps can be in some way retrieved?
The destruction of information was counterintuitive, and it didn't match the rest of the things we knew. In all parts of physics, we had a situation where information doesn't get destroyed. So it was a bit puzzling.
This debate furiously went back and forth up through the 80s and into the 90s when people finally began to articulate this new principle, this holographic principle. And what it said is that all the things that were falling inside a black hole were somehow captured in a preserved image at the horizon itself.
So if the information is not lost on the surface, the information is not lost inside because they are equivalent.
All of the information about those objects, what they were like in their three-dimensional existence, was preserved or encoded on the surface of the black hole. And that's a little bit like a hologram.
Well, that suggests that maybe that idea may apply more broadly to the universe as a whole. Maybe the three-dimensional objects, us, everything in the world around us, maybe all of the information in these objects is carried, is smeared around a distant two-dimensional surface that surrounds us, and we're just in some sense a holographic projection of that distant data.
The holographic principle tells us something quite astonishing. It says that our ideas of volume, of the real world in a sense, might be a kind of illusion.
So, are we real or are we just holograms? Let's begin with that. But in fact, let's first of all remind folks that you guys were direct participants in that argument that was described in that film, which I think fairly characterizes the difficulty scientists have not only in sort of grasping and fully understanding this holographic effect principle, but also explaining it. Leonard Susskind, what was it like to get into essentially a pretty big cosmological argument with Stephen Hawking? And be careful, because Hawking's one of my wheelchair boys.
Yeah.
And we're really tight. We're really tight.
It wasn't that physical. What was it like? It was fun and it was frustrating. It was incredibly frustrating. Stephen had a view which was very, very difficult to argue with. His ideas were based on very, very sensible ideas. A black hole is a place where nothing can get out of, but things can fall into it. And if things can fall into it and they can't get out, they're gone. But then the black hole evaporates. Stephen had proven that beyond anybody's doubt. And so things fall into the black hole, they can't get out, the black hole evaporates, poof, it's gone, just exactly as Brian said. It was unassailable. There was no way to argue the case. And yet, some of us, particularly Gerard and myself, very, very strongly felt that this really undermined everything that we knew about physics. Everything that we know about physics today, and even much earlier, was based on a principle of physics which is so basic that we sometimes forget to mention it to our students. It's the idea that information never disappears. And I'll tell you what that means. Information means distinctions between things. A hydrogen atom is not a oxygen atom. An oxygen atom is not a hydrogen atom. There are distinctions between these things. And it was a very, very basic principle of physics that distinctions never disappear, that they may get scrambled, that they may get all mixed up, but if you start with one configuration and you let it go, or you start with a different configuration which has different information and you let it go, they'll stay different. And Stephen was saying exactly the opposite. No matter what you throw into the black hole, in the end you get out exactly the same thing. It was extremely difficult to see what was wrong with what he was saying. It was even harder to make him understand that there had to be something wrong with what he was saying, so it was very, very frustrating. But at the same time, it was very exhilarating to come up against this basic problem of conflict of principles. And if anything can break the impasses in physics, if there are no experiments available, it's conflicts of principle. When conflicts of principle arise, that's when major new paradigms can shift.
That's the excitement. That's really the excitement. Gerard, explain to me why this problem with Hawking, this, the information can't go away as it seems as though Hawking's mathematics suggests it does, is different from something like, say, conservation of mass energy, where matter can neither be created nor destroyed. It's different than that, right?
Yes, it was a very fundamental problem. And the way I always saw it is Hawking was using quantum mechanics, in particular quantized fields, to derive his result. So quantum mechanics went in as starting point number one, and then general relativity and everything else, and they used all that to derive that black holes radiate particles. From that, it was derived that there was information, and there was information disappearing. Well, the fact that information disappears is at odds with quantum theory itself. So he uses quantum theory to derive a result which basically was at odds with quantum theory. So there had to be a mistake somewhere. I shouldn't call it a mistake, because what he did was by itself mathematically correct, and nobody doubts that. But the final result had something in it that couldn't be true. And so this is what in physics we call a paradox. And like my friend Lenny has been saying, as soon as you encounter a situation of this sort in the physical world, we are very happy, actually. If there's a paradox, it means there's work for us to do. We have to clear this thing up. And if you look at the past, you know quite well that when people start to clear up paradoxes, new discoveries are being made.
So you guys are
We've seen
friends.
several cases, and that's why we're also excited about this thing. There's something wrong. The derivation itself seems to be flawless, but there's something wrong anyhow with the result.
You guys are friends then.
Of course we are.
Yeah. Herman, let me ask you a question just about this issue of information, and then I want you to go back. I definitely want you to go back. Why does the universe need information? Why does it need to have this information? Why does a rock need some sort of informational image?
What you call information, we as physicists would just write as terms in equations, right? We think of the physical world as being driven by mathematical formulas. In these formulas, there are what we call degrees of freedom. So things can be this, that, or that. Oxygen or hydrogen, as an example. All these things which go in the equations. And we are used, in particular in quantum mechanics, to the situation that if two things start up differently, they end up differently. That's a fundamental notion in quantum theory. We can't get around that. You can't have two different states ending up after a while to be the same. That violates the principles of quantum mechanics. Now, quantum mechanics itself is not such a sacred theory that maybe there are violations of it, but then we want to know about this. We just don't want to say, well, you know, we have to clear that mess up later. No, the mess has to be cleared up right now. If there's a flaw of this sort in our result, we want to know about it. So what Hawking was saying, two different black holes start out differently. In one of them, a teapot is falling, the other an old shoe. I saw this movie. And if the teapot falls into a black hole or an old shoe falls into a black hole, that's different. A teapot's not the same thing as a shoe. Nevertheless, after a while, they look exactly the same, according to Hawking.
I see. So it has to be a different
We said that violates our equations. That cannot be true. There's something wrong. Something went wrong on the way, and we want to know what it is.
Thanks for referring to that, because I can't tell you how hard it was to get the teapot in the black hole and then to get the shoe. You know?
I
Sometimes
realize
they say,
that.
just get the teapot. We said, well, you got to get the shoe too, and that was sort of really hard. Herman, please.
Right, okay. Let me first follow up on sort of because you were asking how was it to have this debate with Hawking. That was kind of your question. Maybe I can tell a little anecdote about how it was. In part, it was, of course, all about science, and we're all friends, even if we disagree about the science. But Hawking is a very special person where he can think very deeply about questions, but he also has a handicap. He cannot speak, so he has to speak with this by typing words. And then sometimes the debate would go like this, then indeed an argument would be given, and then Hawking's response would be one word: rubbish.
Very hard to argue
And
with.
that's very hard to argue with.
Yeah, and when I say rubbish, nobody pays any attention. You know.
But when Hawking says rubbish,
it's
silent, and you've lost the argument at that point.
Capital R. Yeah. It's a big font there.
Yeah, right.
When Hawking says it. All right, so Hawking says rubbish to you. Do you like go home and tell your wife, Hawking said rubbish to me, what do I do? Or do you like go to the blackboard, or you just sit down at the computer? What happens?
You go on with, because you believe in your argument. The other question about information, the thing that I like sort of as a way of explaining what information is. We live right now in the age of information. This is the information age. And, but the type of information that we're talking about here, you say, well, it's more complicated, but one way of imagining what kind of information we're talking about is, I like, again, the movie The Matrix, where, again, there's this virtual reality where, and actually I had kind of nightmares myself when I was young. Okay, well, what if the whole world is just a thing that's being projected on my brain? Or actually for all of us, we're sitting here in this room, and who knows, maybe it's just a computer that makes us believe that we're real. And the kind of information that we're talking about is really sort of what is inside of this computer. Imagine you make this hall here with all the reality of being able to do experiments, things fall, you collide things happen exactly the way we think about them as happening in physics, but it's all just zeros and ones in a computer. And in principle, you can quantify how many terabytes, how many gigabytes, how many, I'm not sure if I forgot what comes after gigabytes, but there's information in that computer, and that's the kind of information that we're talking about.
So when you say information, you say that physicists believe and cosmologists believe that it is possible to map every aspect of reality that we are experiencing here into some sort of stored code that specifies precisely everything that's happening here, what people smell like, who is mad at who's wearing like dirty shoes, and what they're even thinking about.
Right. You can imagine that that's the way it goes.
Now, is that something scientists are imagining, or does quantum mechanics insist that that must be so? Raphael?
Quantum mechanics, in a way, is based on information. It's a theory of information. The way that we would describe the world, the room being full of people or not full of people, an electron being in this place or in that place, these are different states, as we call them. And it's as if you put one letter on the page or you put a different letter on the page. It conveys information. So where a particle is a way of conveying information. And in fact, quite literally, when we write something on a page, we put particles in particular places, and we thereby convey information. It's not very efficient compared to.
Let's explore that for a moment. Victoria, do you have Raphael's slides? Put up his first slide here, because as someone who studied mathematics poorly, the understanding that I had was that as you go. Say you're looking at the coastline of Massachusetts, and you're looking at it from a satellite, and you see one line, but then you come closer, and then you begin to trace every little indentation, and then you even get closer, and you trace even any more indentation, and try to specify down to the atomic level that the amount of information in the line that traces the coastline is actually unbounded and infinite. What is it that you've discovered?
Well, that it's not. It's not infinite. There's a limit.
And so how do we begin with this picture here?
I think there's one important thing that maybe we need to say in order to get from the black holes to this.
Sure.
I was actually not part of this debate with Hawking. I became his student 2 years later. But
you look younger as a result.
As a result, yes.
It's certainly aged these gentlemen here.
So
Incidentally, the reason we're ordered this way is we came in, we figured Raphael could walk the furthest.
Right. And we decided we're just going to leave you here when we.
And Hawking couldn't be here, so you got me. So,
yeah. He was here last year.
Yeah.
Anyway, so these gentlemen had, the crazy insight that when information is dropped into a black hole, it is not in fact lost. Even though naively you would just think, okay, now it's in this black hole, it's somewhere, but we can't get to it. They insisted that you still have to be able to get to it, which, Lenny made it sound so easy, but it wasn't that obvious. It was an incredible intuition. And for that to be true, that if you throw a phone book into a black hole, that later on you can figure out whether it was the New York or Chicago phone book, two amazing things have to happen. First of all, Hawking had to be wrong about the idea that no matter what you throw into the black hole, the same thing comes out. It's a very loose way of putting what he said, but that's the basic way information would be lost. A second amazing thing had to happen. which is, it takes a long time for a black hole to fizzle away and disappear and potentially return information to you, supposing Hawking is wrong. And in the meantime, you've got this big fat black hole sitting there. And what had to be true was that while the big fat black hole is sitting there, that black hole itself contains information while it's still sitting there and hasn't fizzled away yet.
All right, so the question...
for that to be true, there had to be a limit on how much information there could possibly be in the region that was occupied by the black hole, because you could presumably always convert that region into a black hole.
All right, so let's back up for a second. So Hawking suggests that the information is gone. You say that can't possibly be true. Hawking says rubbish. And then you go about saying, well, no, we're going to find where that information actually is. Leonard, and before we get to Raphael's slide here, where did you find, or where did we find that information that Hawking says is gone in the black hole is actually stored?
Okay, so one of the things that we found is, I'm sorry to say this, John, but that turned out to be a bad question.
Okay.
That in a certain sense, bits of information don't necessarily have locations, or at least they don't necessarily have locations which are objective and the same for everybody no matter how they're moving.
Okay, I'm all about that question.
The notion of a bit of information is a good one. We believe it, we believe distinctions exist and distinctions persist. But the notion of where that bit of information is located turned out not to be a good, what a physicist would call invariant question. It might depend on who was looking at it. Now, let me give you an example of where it is a good idea. If an atom decays inside the sun, everybody will agree it happened inside the sun. It doesn't matter if you're moving relative to the sun, it doesn't matter if you're far away, if you're nearby, everybody will agree. If they do the calculation, they see what comes out, they'll agree. The atom decayed inside the sun, if the thing happened inside the sun. Black holes are different. And what we found out is the whole notion of whether something happens inside a black hole or if it happens just above the surface of the black hole, the surface meaning the horizon, is a question which is observer dependent. Somebody who falls into the black hole may have all of the experiences of seeing the event happen well in past the horizon. Somebody standing outside the black hole will reconstruct out of the Hawking radiation that event actually happened outside the black hole. So the answer to your question is we didn't find out where the information was. We found out that it was an improper question, that bits of information don't really have locations in that sense.
And how do you know they weren't destroyed if you couldn't find them in a particular location?
Well, eventually, a lot of the power of string theory and other mathematics came to bear on it and confirmed that there was no expectation that it would be destroyed. But as, can I call you Gerard? It's so much easier. Okay. As my friend Gerard here says, I spent years learning to say Gerard, but never mind.
I'm totally fine with Gerard.
Yeah.
Totally fine with it.
God, I'm 71 years old, and I forgot what I was going to say.
No, but you were saying that the issue of where it was and the invariance of the question meant that, or the variance of my question meant that you wanted to basically change the nature of the inquiry.
Yeah, right. But you asked me how we know, and I think the answer was given by Gerard, that so much would break down in physics. The whole structure of everything we know about physics would break down and disintegrate if even you open the door a tiny little bit for the idea of information to be lost. Once it can be lost, you can promote that and make it worse and worse and worse and worse, and eventually the whole structure of physics as we know it will break down. There are some things you can't have a little bit of. You either have it or you don't. We all know about pregnancy, but let me give you another example. In mathematics, can you have a theory, a theory which means a mathematical structure, arithmetic or whatever? Can you have a theory which is approximately consistent? It's almost completely consistent, okay? Well, you might have some structure, some set of axioms, and you derive you let your computer run and derive 10,000 theorems from it, and it say, oh, it's approximately consistent. Only 4 of them were inconsistent with each other. Well, no, a mathematician would come and tell you, once you have any inconsistency, you can use that inconsistency to promote it to anything is inconsistent with everything else, basically. I think the same thing was true about information loss. Once you had it in any form at all, you could imagine situations where it would undermine basically all of physics. And that's what, I think that's what Gerard thought, that's what I thought, and it's what Stephen didn't think. So we sort of battled our heads against the wall for a while.
All right, so how, in my imperfect question-creating way, can we get to the point of either, if not where was the information, how did we learn conclusively that it wasn't destroyed, and that if the phone book went into the singularity, that there was a way to find out if it was Chicago or Amsterdam or, Soweto?
Whenever I encounter a situation like this, I try to approach it from all possible angles, particularly angles that my neighbors here would not be prepared to look at, to see what can be done. We have, as I said, a paradox here, and the resolution must come from a totally different point of view than previously. Now, one thing was that quantum mechanics was used to derive the result, and quantum mechanics somehow failed to agree with the final result. There was something wrong. So my attitude was, we start from the other end. Now let's assume that the black hole as a whole agrees with anything we know about quantum mechanics. That means information in is equal to information out. It's that simple, basically, in a quantum mechanical sense. So that ought to be true. As soon as you believe that it is true, it's a relatively simple calculation to find how much information there is in the black hole. And you do that calculation, you find the amount of information in the black hole is exactly equal to its surface area. It's like putting bits and bytes of a computer memory on the surface. Every bit, every byte of information occupies a very precise amount of surface, which you can calculate relatively easily. And that tells you that big black holes contain lots of information, small ones contain a little information. Still enormous amounts in any absolute sense. But that was a very clear conclusion how much information there is in the black hole. But the question where the information is something else again.
All right, but let me just back up here. So all you got, if you got your black hole, to study, at least not to find where the information is, but to figure out if there is a quantity of information that could be sufficient to specify what goes on in this black hole. You've got your surface.
Not just sufficient, the exact quantity itself.
Exact, okay.
There's a few bits hanging around the side, but apart from that, the total quantity of information is very precisely calculable.
But all you've got is the surface of the black hole.
Yes.
And so you've got to test, could there be enough information on the surface to specify what's gone into this singularity and what's happening beyond this event horizon? That's the question, right?
Well, the question was answered by this assumption that the black hole should obey quantum mechanics. Once you make that assumption, you find that not only the information of things that went in and out of the black hole, but everything in its vicinity should be mapped onto its surface in bits and bytes. It's like saying that the surface is a hologram of the immediate surrounding space-time.
So a x-dimensional object can specify an x plus 1 dimensional object. Yes. Are you getting this here? Is this working for you? We're cool, right? All right, good. You're all with us. Okay.
So the surface is two-dimensional.
So surface is two-dimensional.
But the surrounding space-time is three-dimensional.
Which is exactly what a hologram does. You got your two-dimensional Star Wars movie and your three-dimensional looking Princess Leia, who, by the way, did have a prom date, I believe. And so, but is that an illusion? In perspective, it's basically you're creating an illusion, or is it actually a one-to-one mapping of all the information of the reality onto the 2D surface that gives you your 3D reality? Herman?
Yeah, again, talking about the mapping, then we don't know exactly how that mapping works at this point. But I would say that the principle that turns out to be very powerful in this context, I call it the Rumsfeld principle. And it's basically saying, well, it's better to deal with known unknowns than with unknown unknowns. So
he was bad at all of them, by the way.
Yeah, right.
Yeah.
So the unknown unknowns are stuff that you lose and you don't know that you lost it. If you throw something in a black hole, for all practical purposes, you've lost it. You've lost the information. But what we're talking about is actually that we know that we lost it. Again, I don't remember what I ate for breakfast yesterday, but I knew I had breakfast. So at least I know how much information I lost by having a bad memory. And so the fact that we could quantify how much information is in the black hole and that it's measured by the area, that turned out to be surprisingly the key insight. So knowing how to quantify what you don't know is a deep principle.
All right, I think, yeah, that's actually starting to work for me. Let's forget your slides, Raphael, for the moment, if you don't mind, and go to Leonard's slide, which really gets us from this idea of there's a bunch of information and it maps into something that we might think of as a three-dimensional image. Victoria, can you put Leonard's first slide up? Okay, what is this?
First one? That's a microscopic picture of the film of a hologram, which in fact I made up myself with Microsoft Paint, so it's a fake. But it's about what it would look like. It's about what, if you look through the microscope at the film, not the thing that is being described by the hologram, but by the piece of film itself, it would look approximately like that.
And so then if you put light through it in some particular way.
Right, well, let's first. It's got some information in it. It's all scrambled. It's impossibly scrambled. You can't look at this and see what it is.
Anybody, any guesses what the image is there? Anybody want to guess? What? Leonard Susskind. Good.
Donald
guess down here. Okay, great. So
it is a fake.
Anyone say puppy? Anyone say puppy? Little horsey? No horses. Okay, all right. Let's see.
Well, okay, go to the next one.
Let's go to the next one. Here's the stand by, folks.
All right. This is another fake. I also drew that myself.
All right.
All right. So if you do the right thing with a hologram, namely shine light on it and so forth, it'll reconstruct an image.
So you got the flashlight. Maybe this is obvious, but the flashlight going through the film, and somehow the information in the film recreates the 3D image of the clown smoking the cigar.
But the interesting thing about it is that the clown is three-dimensional. You can go behind it and you can see whether he has hair on the back of his head. You can go underneath and look at the chin underneath. In fact, if this hologram had been made not with ordinary light, but if it had been made by an NMR scan, you could have coded on that boundary, on that surface, you could have the interior, you could have all your guts and blood and everything else, bones. The entire full three-dimensional structure would have been mapped. You used the word mapped, and it's a good word. Mapped onto the boundary, onto the film. And the important thing is not that you shine light to reconstruct it, but that the information about the clown is equally well and in fact, in some sense, better described, more accurately described, more precisely described by the little dots and dashes and structures that are entirely scrambled, totally impossible for you to just look at, but it's there. It's there in that film.
It's there. And as you say, you can add detail to that informational film infinitely, or is there an upper limit?
Okay. So in the world that we're talking about, which is the real world, there's a limit. No more than 1 bit, and that means a plus or a minus, 1 little dot per Planck area. The Planck area is a certain unit of area that's made up out of the fundamental constants of nature. It happens to be about 10 to the minus 33 centimeters on a side. It's far smaller than anything that physics studies experimentally, but no more. Where'd it go? It disappeared.
Black hole, something.
Yeah, they went in the black hole. Yeah. No more than 1 bit, that means a black dot or a white dot, per Planck area.
All right, so let's just back that up for a second. Just as you need a certain amount of resolution on a piece of standard film or a digital CCD chip to produce an image that's recognizable of your lovely pets or your kids or something like that. In physics, 1 bit of information, is it a traditional bit, as though?
Yes, it's a yes or no question.
A yes or no question. So
up or
a
down,
0,
or
1, a
heads or
0,
tails.
1 bit
Yeah, 0, 1.
is necessary to specify a Planck space, which is an infinitesimal but measurable a little chunk of space.
Well, beyond our ability to measure at the present, but yes.
All right.
And so what it says, I mean, in essence, what it says is this entire room, everything that's in it, can be in principle described mathematically in terms of degrees of freedom, structures on the boundaries, on the walls of the room, with never needing more than 1 bit of information per Planck area. That was very radical. That was very surprising because people had always associated information with volume. We have another picture, but maybe you want to go around.
Well, let's go. No, let's go to. This is the pixel.
The pixels and the voxels.
Okay, let's do the pixel voxel. That's the next 2 slides.
Not sure which one
Victoria.
will come up first.
First, the pixels. All right, this is obviously a 2D.
Can we jump to the other one first?
All right, let's do the voxels first. Okay.
All right. There's the room. If you like, there's the room. And I'm going to describe the room, everything that's in the room, by dividing it up into little tiny cells. A cell, let's say, no bigger than an atom. And what can we ask about a cell? We can ask, is there or isn't there an atom in it? Of course, we can ask what type of atom, but let's ignore that. Is there or isn't there an atom in it? And if we didn't have to worry about the type of the atom, that would be a complete description of everything that's in the room. And so there would be one decision for each voxel. A voxel is a word that means a little cube. There would be 1 bit of information per voxel. It's either empty or it's full.
All right, so we've divided up this room in each Planck space.
Well, I was talking about atoms, but yes.
All right, in each bigger than a Planck space that we've decided to choose, we're asking the question, is there an atom in there? And there's a yes or a no answer to that. And we reconstruct the entire space in information terms in a cube like this.
Right.
And we got someplace there are atoms, someplace there's not. I would say in this room would probably be a lot of yeses, probably, right?
Many more no's than yeses.
You think?
Oh, yeah.
Well, that's
the room
right.
is
Space
empty.
is mostly empty.
Yeah, the room is almost all empty space.
It annoys me to hear that always, but yeah.
Well.
Anyway, okay, so now that's the 3D.
Yeah.
So what's the other picture?
Well, what we found, in essence, is that's too much information. No room can ever have as much information as is implicit in this picture here. The amount of information that it takes to describe the room is more like this picture here. 1 bit of information per surface area. So I like to say the world is pixelated, not voxelated. The world is made up, or the degrees of freedom of the world, the most accurate description we can ever have is in terms of a number of degrees of freedom which is proportional to the area and not the volume.
So it's actually the reverse of our intuition, and
Very much.
Gerard, help me out here. So we like to think of, gosh, you know, movies are great, but wouldn't it be fabulous to have IMAX 3D? In fact, what physics says is you can get all the information in your 3D high-res reality world on a 2D surface.
Let me just, one thing before I want to get these guys.
Yeah.
The only thing is that the 2-dimensional description is going to be monstrously scrambled, very difficult to decode, very difficult to see what it's a picture of. That's the cost of coding information in 2 dimensions instead of 3.
Right. As a mathematician, your first reaction will be there's much less space on a 2-dimensional surface than in a 3-dimensional world. So your first reaction is that can't be right. We will be missing enormous amounts of information if we try to scramble everything on a surface. However, you have to remember that this is the Planck length, which is extremely small for all standards. 10 to the minus 33 centimeters is extremely tiny even in units of elementary particles. So even this looks at first sight to be very little information. Actually, it is enormous. It's gigantic. But on the other hand, you have to realize that not only what's in this room should be mapped on the surface, but the entire universe can be mapped on the surface. That's even more gigantically crazy because you would think that the surface of the universe would be much smaller than its volume. But again, these Planck units are so small that still you have enough information on the surface to specify everything that goes on in the universe.
Well, I mean, it's so counterintuitive. I mean, every time I go into the Holland Tunnel, I wonder how all of New York could fit in here. But in fact, that's kind of what you're saying.
Precisely.
So it is very, very counterintuitive.
lot more than-
So you come up with these mathematical conclusions that are very robust and sound, and you can defend them. I mean, do you go back, Herman, to Hawking, and then does he say, sorry about saying rubbish, or I guess I was wrong about the rubbish?
To his credit, he has started changing at least his opinion, and he accepts a lot of these ideas. Einstein, for example, had a much harder time accepting quantum mechanics. I don't think he ever did. But Hawking, I think he realized at the time when he was putting this paradox forward, that by stating the contradiction that was in black hole physics, he realized that that was a way of making progress. And of course, he liked annoying his colleagues, which is sort of what he was doing by making this particular claim. But he put us to work. And then by the time that answers came forward, he had this bet with one of his colleagues that I think it was for a year-long subscription to Playboy. But in the end, the colleague decided to give him a nice book instead. Because the bet was settled, and then Hawking admitted that information was there, and so that's...
Well, the whole 2D, 3D thing, if you bring Playboy into it, is a whole, that's a whole other information space I don't even want to think about. As a much younger researcher, Raphael, what excites you about the holographic principle in terms of, and we're going to get into its controversy in a moment, in terms of what it begins to explain about other problems in physics?
I think what's exciting to me is that the only way that information could possibly not be lost when a black hole forms and then evaporates was for there to be a completely universal relation between the information content of a region and its surface area. In other words, there was a relation between surfaces in space-time, which are described by gravity theory. That's the realm of Einstein's general relativity. Surfaces surrounding certain regions. Those surfaces, their area specified how much information could be in the region that was enclosed by them. That turned out to be not quite the right way of stating it, but that was necessary if information was not going to be lost in black holes. In other words, it led to a statement about how much information there is in the world that was completely independent of what you were using to encode the information. It didn't matter whether you used letters on a page or atoms or strings or quarks, whatever your favorite physical ingredient was. It was a statement that was completely universal. If information was preserved, then we were learning something about fundamentally how much information there is in the world.
Well, even beyond that, we're learning that...
Let me just maybe say one thing, just to put that in a context. It's actually not very difficult to understand why this is so. Very roughly speaking, any place like this room can be converted by crashing some shells of matter into it, into a black hole that has the same surface area as this room. And we know how much information the black hole contains. So if information is not lost, that means that the information in this room, no matter what was in here, had to be less to start with than the information of the black hole, or at most equally much. And so it's completely universal. You don't have to know what we're made out of. You don't have to know what the fundamental bits and pieces of physics are. You already know how much information there is. And so it's a deep relation between the two things that we don't know how to put together, gravity and quantum mechanics. Quantum mechanics is about information. Gravity is about geometry and surfaces.
But is it true, or is it a distortion to say, and again, for me, for a moment here, the idea of going to the black hole seems to confuse the issue, because the black hole is interesting because the way Hawking described it, information would be destroyed. That produces the controversy, which poses the question, all right, what is the relationship between information and all of the universe?
That's exactly right. It's exactly right. It was one of those questions where, people were just asking an incredibly interesting question, and as a consequence of resolving it, stumbled upon something that was much more general and didn't really just hold in this particular context of the black hole. In the end, you can throw the black hole away, and you're still left with...
Because I think most of the people in this room, the encounters with black holes are, monthly at best. So let's just say, because of the black hole thought experiment, controversy, argument with Hawking, we have stumbled upon or discovered or now see that a fundamental feature of the universe is that a two-dimensional space of information specifies everything in our universe.
Well,
something like that?
Initially, it wasn't clear how to apply this to the whole universe. Again, the context in which this was discovered was a very specific one, where you're far away, you throw some elephants into a small region, they form a black hole, and then it evaporates. And you want to ask the question, by looking at this Hawking radiation that came out, can I figure out if it was elephants or zebras that made the black hole? Now, that was resolved, I think, by now, pretty definitely. We can look at this, but our universe is nothing like that. Our universe is not like a black hole. Right. Our universe is not a place where you can go far away and study Hawking radiation coming out. And nevertheless, it turned out to be true that this was just the tip of an iceberg. There's a completely universal relation between information and area of surfaces. At first, it seems like that can't possibly be true. For example, if you don't take the viewpoint of the person who waits for the Hawking radiation to fizzle out of the black hole and then looks carefully at the information that is in it, suppose that I fell in with the elephants or with a star that was collapsing. Well, that star has some information in it. As it's collapsing to form a black hole, that information can't disappear. But we know from just solving Einstein's equations that the surface area of the star becomes smaller and smaller and smaller until it's zero at the very end when it hits the singularity inside a black hole. So it seems clear that the amount of information of the star, whatever it is, at some point is going to become larger than this smaller and smaller and smaller surface area of the star as it gets more and more compressed deep inside the black hole. So then does this mean that this was just some fluke? It's something that applies to particular observers who live far outside a black hole, and there's actually no general relation between information and surface areas? Well, it turns out no. If you state the relation in just the right way, then it's true even deep inside a black hole or in regions of the universe that are very large. And the way you have to state it is actually in a much more physical way. Instead of saying, how much information do I have at this instant of time when my star is really small and has very small surface area, how much information is there still inside the star? You have to ask, well, if I took a picture of that star at this time, just before it got completely crunched into a singular place in space-time, if I took a picture of it, how much of the star would I see? And it turns out that you don't have enough time. The light doesn't have enough time to traverse the whole star before everything gets crunched into the singularity and the game is over. You have to actually calculate this. You have to take my word for it right now. But
I'm taking your word for so much, pal.
But the point is, if you ask, okay, what can actual light rays see? How much information can they see? Right. Light rays that come out of the area in question, and it makes absolutely no difference what area you pick, anywhere in the universe, any shape, doesn't even have to be closed. What those light rays see is some piece of the star in this particular example, and by some conspiratorial miracle, it's always less information in that piece of the star than the surface area you started from. It's a much bigger conspiracy of which only the sort of tip of the iceberg was discovered in the context of black hole.
Well, it's a little bit like uncertainty in the sense that if you try to measure, you're only going to get a piece of it, but that doesn't affect the existence of all the information. It's all there. The fact that you can't get it or don't have a big enough camera is your own personal psychological problem. It doesn't affect the universe at all.
Well, indeed, if you wanted to ask how much information is there in the universe, then again, it's actually very useful that information is sort of encoded on regions that are seen by light rays. You could just ask, well, how far? What is in our past? What is in the region from which light could have reached us up until now? And that region is bounded by basically light rays that are just barely making it to your eyes right now, and they've been traveling for billions of years since the beginning of the universe. And those light rays, well, if you follow them back, of course, they come from a larger and larger region as you follow them back that's farther and farther away. But at some point, their surface area actually becomes very small again when you follow them all the way back to the Big Bang, because everything is small at the Big Bang. The universe is basically contracting to a single point at that point. And so there's a largest area which tells you how much information there is in the universe, somewhere between the Big Bang and us, that is spanned by these light rays. So we can say exactly what the maximum amount of information.
So is it the case on some level that the function of our senses? I mean, Galileo looked at light rays and drew some conclusion about the universe. Are tiny sort of instances of the universe conveying in information something that's much bigger, that we're now extrapolating to extreme states of the universe, either in terms of the very beginning of time with the Big Bang or the sort of end of matter in a black hole? That they're part of the same story a little bit?
Well, the interesting thing about the holographic principle, I think all of us probably agree on this, is that it's a statement that can be made in a situation where we think we understand physics very well. The area that describes how much information there is in the universe that we see is not an area that lives somewhere very close to the Big Bang where we might not trust our equations. The area that tells us how much information there is inside a black hole is not an area that's somehow close to the singularity inside the black hole, which we don't understand as well as we would like to. These are areas in regions of space-time that are arbitrarily well understood. They're completely harmless. They're, Einstein's theory applies.
Harmless is good.
Harmless is always good. I mean, I still wouldn't jump into the black hole, but
right.
They are very, well understood areas. The whole statement takes place in a regime of physics that we completely understand. But what we don't understand ultimately is why it is true. It seems like a conspiracy. Every time you check, it works out. And I think that by itself, was always a huge piece of support for the idea that information isn't lost. All these miracles happen for information not to get lost. It'd be funny if it was at the end. But you have to do it on a case.
Funny.
Your sense of humor is not so
I know, yeah, right. Well, I love apocalypses like the next guy. But Hermann, what is the counter-argument here? I've got sort of two questions. One is, what is the counter-argument? Who persists with the idea that this holographic principle may be fun to talk about, but in fact doesn't really help us, or there's another explanation?
I wouldn't necessarily say that maybe that people have a counter-argument. But right now, you can state it as a principle because we have indications that it's there. But again, it's basically, from an intuitive point of view, it's absurd that this would be true. Because again, if we want to describe what's going on, for sure, we're going to tell, okay, well, something is happening here at a given time, or something's happening there. So essentially, the information that you use to describe things, for sure, grows with the volume. And indeed, the equations that we're using to describe physics indeed have all those properties. So right now, we don't have a real way of understanding how this is really true. So we know we have hints that it's true.
There's no evidence?
No, we don't have a mathematical theory that precisely describes how it is. We have strong evidence that it's true. And I think, so there were early times, say in the early 90s, where if you would, and I think there was a conference in the early 90s where there was a vote. Okay, how many people were actually believing that information was lost? And then more than half of the hands went up, and it was only a small group of people that were saying, okay, well, we don't believe that information is lost, and it was only a couple of
the rubbish group.
There was the rubbish group, and then there was
right. And now the rubbish group is bigger. Almost the whole room.
Yeah, if you call us the rubbish group.
Well, you were then. You were then.
Yeah, we were called rubbish, that's correct. And proudly so.
How, I want to go back to this information, and I actually want you to go through those slides that I've seen before, which I think are fascinating. But Gerard, let me ask you, is information a particle in the sense that it's like matter? Is information akin to being like electrons, protons, quarks, antimatter? Is it some sort of parallel phenomenon that goes along with reality, or is it something fundamentally different?
No, actually, I think it's about time that we start to disagree with each other. And
No.
so I want to, no, you think so?
Starting to get good.
Because I want to bring in a notion which hasn't been put forward yet, the question of dynamics. You know, when I first saw people windsurfing, I loved also to go windsurfing. So on one day I thought, I'm a theoretical physicist, I can work out how to stand on the board, how to hold the sail without falling over. And I worked it all out, and I stood on the board, I could hand the sail, and I didn't fall over, and I went any direction I want. Except I only solved the static problem. I didn't solve the problem, what happens if a big wave comes, and what you have to do if you want to make a sudden turn. This I never solved, so whenever that happens, I fall over. Now here the problem is the same. So far we've been discussing this static question. What is information, where is it, and so on. And you can discuss it at length. But there's something else in physics, the dynamical question. How do things evolve in time, and how do we phrase laws of nature? And now we encounter a deep and fundamental problem, which is the world looks to us three-dimensional. If I make a disturbance here, like I'm saying something or I'm shining a light, the disturbance moves with the speed of light or slower to its environment. And it never goes faster than the speed of light from here to a point far away in the universe. That is a fundamental three-dimensional property of the world as we know. And it has been tested very, very accurately in all branches of physics. It's a very fundamental principle. Not only that disturbances move with a certain maximum speed, it also has causality. That is, whenever you cause some disturbance somewhere, its effect never goes faster than the speed of light, and it certainly doesn't go back in time. Now, this principle we would like to keep. And now holography is standing in our way. It's not doing the thing we want. If my friend Lenny here is right, and information on the two-dimensional surface is completely scrambled, how do you explain it? If you make a disturbance here, the disturbance doesn't spread faster than the speed of light. How would Leah, when she moves her arms in the hologram, how come that the disturbances don't move faster than a given speed in this hologram? There's still something basically wrong with the idea. And that
Why would they have to move faster than the speed of light to work?
That's relativity theory, and relativity theory works extremely well. We don't want to give that up too easily as a fundamental principle. After all, relativity was also a principle that went into Steve Hawking's derivation. If you throw that away, you're throwing away black holes as well. So life isn't that easy. There's a problem here. So how do we address that? And then I'm coming back to quantum mechanics. We say, well, we used quantum mechanics from the beginning until the end. There's something not quite right about quantum mechanics. And I've been thinking a lot, last decades basically, about there must be something underneath quantum mechanics, some more basic mechanical system that explains why the world that we encounter today looks like quantum mechanical. That could solve this problem, because it could be that in a pre-quantum world, the world is three-dimensional. Information gets lost all the time. In fact, a suspicion I have, and I'm practically the only one in the universe today that has a suspicion that there's an underlying theory in which information gets lost to such an extent that if you have a bulk of material somewhere, so much information gets lost that the only thing that you can retain is what sits on its surface. And that is the reason why, information-wise, you have such a thing as a holographic principle. The only amount of information that you can keep if you have a bucket of water is what sits on the edge of the bucket of water. What happens inside will eventually get lost. Not according to quantum theory, because you just realize, oh, quantum theory preserves information. But there may be a pre-quantum theory in which this information gets lost.
Now,
this pre-quantum theory could be three-dimensional, and then we might possibly find a resolution of this problem.
So is pre-quantum theory something that happened before the Big Bang, or is pre-quantum theory something that happens before you learn
pre-quantum in the logical sense? It
geometry.
is that there is something there's some fundamental principle lying underneath
so
the principle of quantum mechanics.
I see.
Saying we have molecules, we have atoms, we have things smaller than atoms, but smaller than that are things which might not be quantum mechanical. That is my premature explanation as to how to reconcile the idea that the three-dimensional world seems to be two-dimensional by a holographic principle, yet there is causality in the three-dimensional sense. This is a problem that has not yet been properly addressed, and I think something should be done about this. If we don't, we'll never...
So get to work.
Get to work.
If we don't, right. If you don't, we'll never
Forget
get
homelessness,
a good
you
theory
guys.
about
Come
what
on.
happens at small distances.
Well, let's put that to Leonard. Is there the possibility of a more axiomatic kind of
It's not a question of axiomatic.
All right, but then some sort of more basic state than quantum mechanics?
The answer is I don't know. The answer is I don't know. What you're seeing here is an interesting thing. First of all, I would say it should be clear that this whole holographic story is the most radical thing that has happened to our understanding of space, time, matter, since the invention of quantum mechanics and relativity. It is really something very, very different. Where is it going? What is it going to explain? How do we explain it? Incidentally, we all agree largely on what we've said up till now. And you'll find that in physics in general, probably in science in general, at any given time, there are those things which have been made into established science that people agree on, and that subset they will tend to agree on unless they're screwballs and outside the mainstream of the community. But that once you go past that, once you go even just a little bit past what we really know, you'll start finding it becoming a very, very human subject. A subject with, let's put it this way, good physicists are as variable as snowflakes. Every single one of them is different. Every single one of them has a different perspective. And once you go past that point where we have confirmation, where we do agree, you're going to find that just about everybody has a different view of where it's going to go.
Sure, but that I can understand. But let's focus on the radicalism for a moment, because I think people can understand how relativity radically changed the Newtonian view of reality, in the sense that the straight lines in the Newtonian world actually are curved in certain spaces, and that curvature relates to the force of gravity in some way. And so around stars, space actually bends. That's a radical notion. It's probably only in the last 30 years that that's been internalized to be something that kind of everybody understands. You can't really appreciate The Matrix, movies like The Matrix, unless you sort of understand the sort of relativistic world. How does this notion produce a radical change in the way that we might see relativity?
I think it's still a work in progress, and we don't know. Harad has his view. I have my view. Herman has his view. What's his name over there has his view.
But I tell you, if you go out of this room...
It'll come to you. It'll come to you.
But you go 2 blocks outside of this room, there's a lot of people who have no view.
Yeah, and a lot of people have no views.
Yeah, absolutely no view.
But my own view is not all that different than my colleague over here. It's not that I think there's going to be some deterministic theory that's going to underlie quantum mechanics. I think it is going to inform how we think about quantum mechanics very deeply, and it's going to change in an enormously big way the way that we think about quantum mechanics. That I am sure of. Whether it will be the way that, that Raphael and I have proposed over the last couple of weeks, or the way that Hufter has proposed for years, Herman has his ideas, I think that remains to be seen, and it is a work in progress. I think there will be progress on it. I think when we come back here, maybe not next year, but 5 years from now, there will be more knowledge. But it's very clear we're on the cutting edge of, and on the cusp of, I think, a major paradigm shift in the way the world works.
All right, that's great. Now, how are we doing? We're feeling pretty good about holographic principle and projection, right? Right? And we're feeling pretty good about it, how information is a much more complicated thing than maybe the concepts from our intuition, right? Right? Okay, good. All right, here's a question that's going to put you on the spot. But it relates to your issue of each of you think differently. The physicists are as different as snowflakes. And hopefully they stick around longer than snowflakes. If I were to put a holographic principle T-shirt on each one of you that specified how each one of you represents a particular sense of what's going to happen, what we're going to discover, what aspect that represents your position, what would your T-shirt say? I believe in holographic principle, and it's going to look like blank.
I don't know. I would like have something like I heart HP or something.
Well, that's going to be on the back.
No.
The front is going to have to
Your
be more
ticket to quantum gravity on the back.
So
your ticket to quantum gravity.
So
I mean, why do we call it a principle? Like, you know, I think the positive spin, the most positive spin I can try to put on this, and I am being optimistic when I say this, is compare this to the equivalence principle. The equivalence principle is something that Einstein recognized, you know, a huge conspiracy in nature. Why do all objects fall at the same rate? You know, different particles with different charges do not get attracted to each other at the same rate. But with gravity, for some reason, everything gets attracted in exactly the same way. Amazing conspiracy from the point of view of Newtonian theory. You just have to put it in by hand. It doesn't contradict anything, but it's just crazy. It needs an explanation. So he elevates this observation to a universal principle. You have to find a theory that makes this obvious to start with.
So for you...
And that would have to be quantum gravity, because what's involved here is both quantum theory and general relativity. It would have to be a theory that knows about both. So it clearly is a signpost. Maybe we need more signposts to find the right
But
answer.
for you, holographic principle is a first step towards a theory of quantum gravity that begins to explain what's so frustrating about gravity.
Well, and indeed, what Gerard just said tells us why it's been so hard. You have to explain where this holographic bound on information comes from while not destroying what we know about locality, the fact that I get to know in this part of the room something independently of there. I get to move particles around independently. It seems like you don't have to know what's over there to do something here. There seems to be a conflict here between holography and the way that physics has worked up until now.
On your T-shirt, Herman, what would it say?
I mentioned the movie The Matrix, probably some image like these letters, and there's Nemo, what's his name? The guy who, he goes and he starts flying with anti-gravity. I think that's pretty good. So let me explain why the Matrix. We talked about sort of things not being able to move faster than the speed of light. And I think the people that came up with the name of the Matrix actually had something pretty good in mind there. Because what is a matrix? It's essentially something that relates something that's here with something that's completely somewhere else. So I think indeed that sort of the future, at least of this development, will be that we start actually with information. So information is going to be our starting point. And space-time is not something that we start with. We forget about what space is and what time. And then somehow the information, by thinking about how much information is, what information is doing, then the space-time will, what we call, be emergent. It will come out of just a bunch of zeros and ones. And here's one idea that I think actually I can put it here just since no one's listening and I can just say what I want.
They're listening, I guarantee you.
So
there's no non-disclosure thing.
So we talked about information, and one of the things, by the way, that information tends to do, again, it gets lost all the time, actually. That's called the second law of thermodynamics. The lost information, we call it entropy. Entropy always increases, chaos increases. And that's a fact that's true in our universe, and it's a fact that's true in other universes as well. So it's a very fundamental fact of how things work. And what's probably also true in other universes is that things indeed fall. If you drop them, they'll go down. And it seems that those two facts are very closely related. The fact that information gets lost all the time, and the fact that things fall. So I think that's...
And lost is different from destroyed.
Lost, when I say lost, indeed, it's going to be the known unknown.
Right.
So it's the known unknown, the increase in the known unknowns that's responsible for space-time, for curvature of space-time, for gravity, the fact that things fall.
I mean, what you're suggesting is that, when I forget something, instead of just having a kind of a pre-senility moment, I'm actually participating in a grand march of our understanding of the universe.
Right, that's correct.
Yeah.
That's correct.
I'm loving it. I'm glad I came tonight. Gerard, what would be on your T-shirt or sign that would suggest where you fall on, and I guess probably the pre-quantum theory, the proto-quantum theory might be on your T-shirt. That might be the direction that you would be headed.
Yes, I will continue to ask nasty questions and say, well, you can have this fancy, beautiful idea, but remember that there are fundamental principles on which the original idea was based that you're losing out of sight. And so this was why I mentioned causality, the fact of the order of cause and events. That is, to me, a very primary law or rule of nature, that everything that happens here has its origin in the past. That's what we call causality. There's a cause of everything happening in this world. That's how laws of nature are being formulated. If you don't have that, you can, for instance, go backward in time and you have circular situations in time, like you can go and kill your grandfather if you could move back in time. That's clearly nonsense. Then you get circular arguments and you get chaos in the laws of nature themselves. Nature cannot solve its own equations. That cannot be right. We must have the principle of causality. Now, this is somewhat at odds with this holographic principle. I don't say it's entirely at odds, but there's some tension here. And what we want, the whole reason why we are doing this, why we're making this, all these considerations, is that we want to have a better model, a better theory of what happens in the physical world. We want to explain why the particles that we have today behave as we have seen them and studied them today. And there are many things you understand and many things you don't understand. We have the standard model of elementary particles is a beautiful rigid scheme of all particles known today, and it is marvelously precisely described by this standard model. But there are mysteries in it which we want to understand and solve as well. We are very ambitious. We've made a marvelous theory of nature. It's not good enough. We still know there are blank spots in this theory that we want to fill in. And this is why we are doing this. We want to find new basic principles to improve our understanding of nature. That's what all of this is about. But the only way to understand to improve our understanding of nature is by asking all sorts of nasty questions. Questions our colleagues rather not ask because they're so confusing. Well, let's ask confusing questions anyway and see if we can come close to answering them. Any question that has an unexpected answer might help us go forward and make an improved theory of the world that we live in. That's what the real reason is for this exercise.
And I love this idea that possibly one way of thinking about causality and the forward march of time is as a information state, as a sort of an understanding of the march of time as a set of information that one event leads to another event.
It's a vision that the universe is very much like an information processing machine, just like your laptop or any other computer. I like to view nature as a gigantically big computer that has information going into it and information comes out processed. The processors, they are the laws of nature. The laws of nature say that something happens, some particular configuration goes in, it's being rearranged, and another combination of data goes out. That's how in physics, traditionally, we consider the process of particles touching and scattering against each other. Two particles come like this, they hit each other, and they go off in the other direction. That's what we call scattering, and a scattering process is an important way of describing the laws of nature. What happens when two particles meet? How do they separate? Do they break each other up? Do new particles form? And so on and so forth. So that's a fundamental way of phrasing laws of nature, and that's what we want to understand.
Can I ask you a question on this? Again, if we talk about pre-quantum mechanics, in quantum mechanics we know that at least one of the foundations of physics, quantum mechanics has thrown it out of the window, because one of the foundations of physics was that if you know what's happening at a certain moment, what the situation is at a certain time, then one step later in time you would know what happens next. But in quantum mechanics you can have two completely identical situations that a second later would give you two different outcomes.
That is right.
Is that a principle that you accept, or is your pre-quantum mechanics going to be of the type where you...
It's a principle I accept entirely within the language of quantum mechanics. But my suspicion is, it's only a suspicion, is that quantum mechanics cannot be the entire story. There's something else happening, and you're exactly asking the right question, which is, how come that if two particles reach each other, and in the beginning they were identically the same, and then suddenly they might do either this, or they might do that, or other particles might come out, and all that is described by a matrix, in fact, in the quantum mechanical sense. But nobody knows how to predict which of the possibilities is actually being realized. That, I think, is a weak spot in our present understanding of quantum mechanics. Why is it impossible to predict in advance what will happen? And there are numerous examples of this which are typical for quantum mechanics. And physicists today have learned to ignore the problem, to say, we solve everything, except we cannot always predict exactly what happens. What we can say is that you need all the possibilities to compute what happens after that. So that's a mysterious feature of quantum mechanics.
And you want to embrace the mystery rather than ignore.
Exactly.
A little bit, okay.
They've learned to do that because it is so successful. It works tremendously well in understanding nature. But it cannot, to my taste, it cannot be the entire story. There's something else happening, but at a different level of nature. And my belief is the Planck scale is so much different from the scale of elementary particles that could well be the level at which things are fundamentally different. There you have, if two things scatter, they have only one choice to make, not many, very many. That's the idea of determinism, which people laugh at. When I mention this idea, people just manage to keep their smile away from their faces, but otherwise, you know, as soon as I'm away, I'm sure they're laughing about this idiotic idea of determinism.
Well, we can check some of the comments on the website later.
It's not such a crazy idea, but
it's an old idea.
It's an old idea, and it has proven wrong about 1 million times. But always they prove wrong because they're making very conservative assumptions, and I don't believe those assumptions. So I still think there's a way to get around
the nasty
this.
question.
Very, very difficult, and it's a dispute that's going on for years and years and years, starting all the way back with Einstein and Niels Bohr. All historians of science say Einstein was wrong, Bohr was right, and I believe it's not true.
That's
well, nasty questions fits on a
what
T-shirt.
goes on the T-shirt?
Nasty questions does fit on a T-shirt. That's good. Leonard, yours.
Well, just with respect to what Gerard says, I wouldn't bet against what he says. On the other hand, I just can't see how it will work. But it's those kind of conflicts which get us where we want to go. But my T-shirt, well, if you can't say the Brooklyn Dodgers, I guess I would like it to say the UV-IR connection. Now, the reason I say that is to give me an opportunity to explain something else. Give me 5 more minutes to explain something else, which we will probably all agree about, but which is a very bizarre property of nature, at least if the ideas we're talking about are correct. It's not totally surprising that as you try to get a more and more accurate description of nature, it looks more and more scrambled. To get the best description of nature, you have to account for all the degrees of freedom. And sometimes it's just too much of a good thing. I mean, you know, we know what happens when you try to have too much information. Too much information can lead to a situation where you're just completely confused because you're just flooded with it.
It would be like you mount a camera over the city of New York, you put a light on everybody's head, and over time you specify where they go. It looks great for about 10 minutes, and then
well,
it's
even taking a sharp snapshot at an instant, Too much information will flood you. You know, we know the CIA gets so much information that it doesn't know what to do with, and it's just got too much. It's not too surprising. You know, you'd learn much, much less about a body of water with a surface and so forth if I gave you a description with a table which just gave you the position and the velocity of every single molecule. That would be an impossible thing to deal with. So it's not totally surprising.
You couldn't windsurf on that information. Yeah.
It's not totally surprising that the better you try to do and the better description, the more scrambled it's going to look. What's also new here is something very different than in the other situations. In the other situations, getting more and more information usually means more and more detail about smaller and smaller distances. What I think we now know is that at some point that's going to reverse itself. And what's going to happen is when you look in more and more detail, things will start to look fuzzed out over bigger and bigger distances. And so in the end, the most perfect, the most accurate description and the most scrambled description of something is going to be stretched out over the whole boundary of space. That's called the UV-IR connection. And what it means, UV stands for ultraviolet, and it really just means small distances. IR stands for infrared, and it means very big distances. And we're getting a little bit, I don't say confused, I'm not sure it's confused, but something is happening where as you start to look at a system at more and more and more precision, what you might have thought that you're going to see more and more tiny, short distance, small distance precision, it's going to start getting fuzzed out and fuzzed out and fuzzed out until it's stretched across the whole...
And that's not simply a feature of the camera you're using or the resolution. That is a fundamental feature of nature.
That's a fundamental aspect of physics, that the better you try to look and the more detail you try to see with, the more it's going to be stretched out and fuzzed out over bigger and bigger distances.
Yeah, I want to follow up on that. So at least one of the reasons why we're now more and more convinced that the holographic principle is really something that works comes indeed from string theory, which is my field. And what happens there is precisely if you go through this step of looking in more and more detail at what happens on shorter and shorter distances, you might be interested in say, what happens inside of our nucleus, inside of our atoms, and there's a nucleus, and there are quarks, and there are smaller and smaller particles. And suppose, again, that for a moment you would want to forget about gravity, but you start looking more carefully at what we're made of. And then because of this idea that when you start looking at smaller and smaller scales, or at least at smaller and smaller distances, suddenly you discover that there's actually something new happening. And that something new, at least in terms of your equations, you recognize it as gravity. So the amazing thing is that while you're actually interested in just looking at the smallest constituents of matter without putting gravity in, gravity comes out as something that's sort of inevitable. And to me, there's an enormously deep lesson there, that gravity is something that you cannot do without. Clearly, we cannot do without it. We would not be sitting here. We would be floating in this. But,
although gravity for me and Stephen Hawking is kind of a pain in the ass sometimes, but, which is why we love to forget about it. But gravity is inevitable, but it's also a door to this something else.
It's a door to this something else, but you can get it out of something where you don't put it in. So it's not the starting point. It's the output.
All right. Well, we're gonna have to wrap this up. Let's just poll the audience. How many of you clap if you think that we are just a projection? Clap if you think that we are actually real. And clap if you don't care. You know, I would have thought that would have gotten the biggest clap of all this far downtown. First of all, I want to thank our panel. You've certainly taken us on a great journey tonight. There's obviously so much to think about. I would encourage, if you're interested in these ideas, tomorrow we're actually doing a Rebooting the Universe, another exploration of the universe as an information space at a panel here. I also encourage you on Sunday in the Kimmel space upstairs Mary Seidman and the Keystone Dancers are going to be doing a fabulous sort of mapping of dance onto the Messier catalog and objects in the universe. So this idea of one information space mapping onto another is a theme here at the World Science Festival. I encourage you to explore all of it. Thank you so much for coming, and thanks to the panel.